The whole world held its breath as 4 humans slipped behind the moon, disappearing into a shadow no live broadcast could follow. For nearly an hour, their voices were cut off, their capsule hidden from Earth, while it traced a path that pushed them farther from home than any crew in history. But before that blackout, the crew were already describing the moon in unexpected ways, noting its brown tones, shifting brightness, and the difficulty of observing it from inside Orion's dark cabin. As they rotated observation duties and documented the surface in pairs, the flyby unfolded in real time. In this video, we're unpacking what really happened in that blackout, how a single swing around the far side quietly reshapes our next steps on the moon, and why the most important part of Artemis II may be what comes after the cameras lose sight. Let's get started. Just before the planned communications blackout, Orion approached the moon on a trajectory that would carry it behind the lunar far side. As the spacecraft closed in, mission specialist Christina Koch remarked that, "The more I look at the moon, the browner and browner it looks," reflecting changing lighting and the clearer view of surface texture at closer range. Pilot Victor Glover noted how difficult it was to look from Orion's dark cabin and dim tablets to the intensely bright moon through zoom optics, turning simple observation into a physical challenge in deep space. By then, the crew was about 2 hours into a 7-hour lunar observation period, working in pairs. 2 astronauts at the windows documenting the moon, while the other 2 managed spacecraft operations and other tasks. At a planned swap point, Reed Wiseman and Jeremy Hansen took over as primary observers, with Glover and Koch rotating into support roles, with another rotation scheduled about 30 minutes later to keep observers fresh as the lighting evolved. As Orion swept around the far side, the moon's hidden hemisphere filled the windows, showing rugged terrain, dense cratering, and highlands lit by low-angle sunlight. At closest approach, several thousand miles above the surface, Orion balanced safe distance with meaningful detail while relying entirely on onboard systems during the blackout. Around the same time, the spacecraft quietly set a new record for the greatest distance humans have traveled from Earth, as the planet shrank to a distant sphere on the displays. When Orion emerged, Earth reappeared over the lunar horizon, communications locked back in, and the spacecraft was already on its gravity-guided path home. Although the flyby was brief, it packed in crucial scientific and operational tests. A primary goal was measuring human performance in deep space beyond Earth's magnetic shield, where radiation and environmental conditions differ sharply from low Earth orbit. Artemis II lets engineers compare crew health, workload, and decision-making in this environment to set safe limits for longer missions. The planned communications blackout doubled as an autonomy rehearsal. During this window, the crew relied on onboard systems and training rather than real-time guidance from mission control, mirroring the Independence future lunar and Mars crews will need. At the same time, the precise free return trajectory validated navigation models that use the moon's gravity to bend Orion's path back to Earth, a prerequisite for more complex operations like lunar orbit insertion or docking. Scientific return came from far-side imaging and environmental monitoring. By photographing the older, heavily cratered far side, astronauts captured updated views that refine models of lunar history and early solar system impacts, complementing robotic mapping. Radiation sensors and dosimeters tracked exposure throughout the pass, testing shielding and informing how long crews can safely operate outside Earth's magnetic field. Meanwhile, Orion's life support and communication systems were run at full deep space distances, confirming whether air, water, thermal control, and long-range links can sustain crews on future Artemis landings and eventual Mars voyages. With the flyby complete, attention shifts to what Artemis II unlocks. As the final crewed test before a lunar landing attempt, This mission shows that Orion can safely carry astronauts to lunar distance and back, reducing uncertainty for more complex surface-focused flights. Engineers are now dissecting trajectory accuracy, fuel margins, and crew workload to decide how far they can stretch future missions in duration and complexity, with Artemis 2 data feeding directly into Artemis 3 planning. The blackout period also proved that the crew can operate autonomously when communications drop, a capability that will be essential for later lunar and Mars expeditions. In broader terms, Artemis 2 reestablishes human operations beyond low Earth orbit after decades in near-Earth space, demonstrating that long-distance travel is once again practical and aligned with goals for a sustained lunar presence and eventual Mars missions. Now, Orion's return leg becomes the final exam. Systems are monitored continuously as the spacecraft heads home, culminating in high-energy atmospheric re-entry, heat shield validation, ocean splashdown, and recovery. The mission's data will then be mined to shape hardware, procedures, and risk models for the next wave of Artemis flights. Humans have just flown behind the moon again. Artemis 2 proved deep space travel is working. Now the next step is landing on the moon.